Okay, bringing you back to last week, we had started our discussion of how we analyze the solution concentration. We said there were three methods we would talk about. One was using absorbance measurements. We said that'll work for things that absorb visible light. You can also use it with UV light for things that don't absorb visible light. We won't do that in this course just because usually the UV part of the spectrum, those spectrometers are more expensive. But that can be done. Gravimetric analysis we described last time. That was the idea that you take your solution, you carry out a precipitation to get all of one kind of ion out of it, and then you filter that and weigh the mass of the precipitate. Use stoichiometry to figure out what the original concentration was. Last one we got to talk about is called titration. So, what is a titration? In a titration, you generally have a burette set up, and into your burette, you're going to put some solution of known concentration usually. So here goes a solution of known concentration. And in the flask down below, you're going to have a solution of unknown concentration. All right. And the idea is those two solutions are going to do some sort of reaction. So I'm going to call it just A and B. So I'll say you have a reaction that looks like A plus B makes some sort of products. So let's say the solution of known concentration is A. Solution of unknown concentration is B. We also have names for these things. The solution of unknown concentration, I'm not going to test you on these names, but they're names you'll hear when these experiments are described. Solution of unknown concentration is called the analyte. And the solution of known concentration is called the titrant. So analyte, it's the solution that you are analyzing. And titrant is the thing that you're adding. So they're going to undergo some reaction. A plus B makes products. Maybe there are coefficients here in this equation. But the point is, you need some observable change to happen when all of, say, your analyte gets used up. All right. So the key to a titration is some observable change must occur when all of B, the analyte, gets used up. So the strategy is you add small quantities of A at a time. That's why you use the burette. We used the burette earlier in the year, and it's useful because it has that little valve. You can open it, let a little bit out, close it. Open it, let a little bit out, close it. So what we do is add small quantities of A, small quantity of titrant at a time, and keep watching for that change to occur. All right. So our general strategy is add small amounts of titrant at a time. When the observable change occurs, record what volume of A was used. Question? All right, so the question is, how do you know when B is depleted? It's going to differ for different kinds of titration. So when I say observable change here, I'm being a little bit vague, but just to give you, some specifics. What do you think the most common observable change is going to be? What's the easiest observable change to actually observe when it happens to a solution? Could be a precipitation. That's actually less common. There's one that's more common. Decomposition. Not that I wouldn't expect a decomposition. Usually the simplest one is there's a color change. But there are others that you can't see with the naked eye that you need to measure. So things like pH change. You could see a rapid pH change that could signal that you've reached what we call the end point of the titration. Another would be a conductivity change. So there are different ways to measure this. Most often it's a color change because that's the simplest one. But could be a pH change. It could be a conductivity change. So what that observation is that tells you you've fully depleted B is going to depend on the circumstance. So the student question is, wouldn't the change occur regardless of how much of B is used? Well, the key is this only works in situations where you have a reaction where the change occurs when B is fully used up. So there are lots of reactions or lots of, say, color changes that will only occur once one of your reactants is completely gone. We'll get into the specifics of that in our acid-base unit because the most typical titrations are acid-base titrations. But when you have, say B was a base and we were adding an acid to it, what you would find is the pH is going to stay roughly level for a long time. And then as soon as B gets completely used up, as soon as you add that next drop, you see a big drop in the pH. And so once you fully use up that reactant, you see that observable change. And we have these things called indicators we can put in the solution that will change color when the pH does that jump. So yeah, we'll get into those specifics of like how we actually make that observation later in specific situations. But just know for now that when we've reached that point, we record the volume of A that was used. We call this the equivalence point. Also called the end point of the titration. There's a slight distinction between those that isn't really important for us. So it's called the equivalence point. At that point, if you record the volume of A that you used, and we said we knew the concentration of A, if I know the volume of A and the concentration of A, what can I figure out about A? If you know the volume and concentration of a solution, you can figure out number of moles. Once I can figure out number of moles, I can do stoichiometry. So the key is, now that I know how much A I used, I'm going to use my balanced chemical equation, and I'm going to use stoichiometry to figure out how many moles of B were in my original sample. And once I know how many moles of B, if I know the volume of B, I can figure out the concentration of B. So that's the general strategy behind any titration. You're adding one solution to another. Once this change occurs, you know that you've essentially added equivalent amounts of each reactant. So if you know the amount of the one you were adding, you know the amount of titrant, you then can figure out how much analyte was there. Question? So the question is, at the beginning I said, A, the titrant is usually a solution of known concentration. So what if it wasn't? Well, you always need to have one solution for which you know the concentration. Occasionally you do this backwards. So occasionally you make a solution that you put in the flask that has a known concentration in it or a known number of moles in it. And then you're adding to it a solution for which you don't know the concentration. So occasionally these two roles are reversed, but the concept is the same. The question is, what is the benefit of that? Well, in certain situations with acids and bases, usually you want to have the weak acid or base in the flask. So sometimes if you have a solution of sodium hydroxide, which is a strong base, and you don't know its concentration, you'll put a solution of a weak acid in the flask, and then you'll put the unknown concentration solution in the burette. But that's kind of the exception. And when we cover acids and bases, we'll actually do that titration. There's a good reason for it that I don't want to go into right now. But you always need to know the concentration of one of the two solutions in your titration. Okay? If you don't, then there's no real point to the titration. All right, so simple acid-base titration. In an acid-base titration, you're usually adding an acid to a base or adding a base to an acid. In this case, it says a 25 milliliter sample of a solution of an unknown monoprotic acid is titrated with 0.1 molar NaOH. To reach the endpoint, 11.6 milliliters of NaOH solution is required. What is the concentration of the unknown solution? So take a minute. You're essentially being given, the volume that was needed to get to the endpoint. You're given all the data you need. So try to do the stoichiometry to figure out the concentration of the unknown. All right, I got a good question, and the question was, what does this term monoprotic mean? This came up when we first talked about acids. So mono generally means what? One. And protic refers to proton. Remember, in terms of an acid, what is a proton really? It's an H plus, yeah. So what this tells me is this is an acid that only has one H plus to give away. Its identity doesn't really matter. We can represent it as just HX. And so the idea is that's going to split up and give us H plus and X minus. So if I want to write a balanced chemical equation, which I usually need for stoichiometry, I would say HX, I'm reacting with NaOH. What are the products going to be? H2O or HOH and NaX. All right, to balance this equation, do I need to adjust coefficients? All right, So this is pretty straightforward because it's a 1-to-1 ratio all around. So first step is going to be to take my given quantities and determine number of moles. So I have a 25 milliliter sample of an unknown monoprotic acid. So that's the one that I don't know the concentration of. Titrated with 0.1 molar NaOH. So how would I write 0.1 molar when I'm doing a calculation? That word 0.1 molar, how would I translate that into units? All right, it's 0.1 mole per one liter. So I know there's 0.1 moles of NaOH for every 1 liter of solution. And then I'd say, all right, well, if I want to get to moles, how many liters of solution did I use? I used 11.6 milliliters. So say 0.0116 liters of solution. So I multiply those two, I'm going to get the number of moles of NaOH. What I want is the moles of HX. So what conversion factor will get me to moles of HX? 1-to-1. There's 1 mole of HX for every 1 mole of NaOH. So that'll give me the number of moles of HX. I could do that calculation. I can do that one in my head, I'm pretty sure. 0.00116 moles of HX. And if I want to know what the concentration is, to get concentration, I need moles divided by liters. So how many liters would I divide by? 0.025, because 25 milliliters is 0.025 liters. And so concentration is going to be 0.046. I'll go with my rule of 3 sig figs. Everything in the problem had 3 sig figs. So 0.0464. So acid-base titrations tend to be relatively straightforward in that most of the time they're going to be a 1-to-1 ratio. You can have an acid that has multiple H pluses, or you can have a base that has multiple OH minuses. So sometimes you have coefficients in your chemical equation. More complicated type of titration would involve redox reactions, which often have much different ratios. Any questions about this acid-base titration before we do a redox example? All right. So here's a redox example. Sometimes redox reactions result in a color change once your reactant's all used up. And so you can do titrations involving redox. A 5 milliliter sample of a solution of vanadium-2 compound of unknown concentration is titrated with 0.2 molar KMnO4. To reach the endpoint, 42.7 milliliters of KMnO4 solution is required. What is the concentration of the original V2 plus solution? The reaction between the two is shown below. So this is kind of a fun reaction because this V2 plus is purple, and then the V5 plus is yellow. So you have actually in between you go through a V3 plus stage, which is green, I believe. So the solution goes from purple. I think it goes purple, blue, green, yellow, actually. Goes through this whole progression. And once it gets all yellow, then you know you've reached the end point. So using this information, trying to figure out the concentration of the original vanadium 2+ solution. Okay, one question that I fielded was, what happened to the K? So in this case, the K is actually a spectator ion. If you look at the reaction at the bottom, this is the net ionic equation. You can see why we might not want to use the full equation for this reaction, because even the net ionic equation is pretty long. And so the K plus here is just a spectator ion. We can kind of cross this out and just make this MnO4 minus. So we have our balanced chemical equation. The first thing we're going to do is take our known quantities and get to moles. So using my known quantities, I have 0.2 moles of MnO4 minus per liter, and I used 42.7 milliliters of that solution. So 0.0427 liters times 0.2 moles of MnO4 minus per liter. That gives me moles of MnO4 minus. Then I'm going to use my balanced chemical equation. I see that for every 3 MnO4 minus, there are 5 V2 plus. So 5 moles of V2 plus for every 3 moles of MnO4 minus. And so I can figure out the number of moles of V2 plus. How many moles of V2 plus were in my sample? .0142 moles of V2 plus. And then I wanted the original concentration. So the concentration of the V2 plus is going to be number of moles divided by number of liters. And it was a 5 milliliter sample, so that's 0.005 liters. So that times 200 is going to be, what is my concentration? Huh? 2.8. All right, yeah. Let's go with my rule of 3 sig figs. 2.85 moles per liter. All right, that's a pretty concentrated solution. Now I want to point something out. If we had not been given the balanced chemical equation, in a redox titration, you don't necessarily need a fully balanced chemical equation, because in each case you're going to have one thing that's getting oxidized and one thing that's getting reduced, right? So in this case we had MnO4. We just need to know what it's turning into. It was MnO4 minus turning into Mn2 plus, and then we had V2 plus turning into V5 plus. All right. What's the oxidation state of Mn in MnO4 minus? Well, each oxygen's -2, so this is -8, plus whatever manganese is going to be -1. So manganese starts out at +7, and it's going to +2. So how many electrons did it need to gain? 5. It's had to gain 5 electrons. Vanadium is going from 2+ to 5 plus, so it had to lose 3 electrons. So what that tells me is, if the vanadium's losing 3 electrons, the manganese is gaining 5, they're going to have to come together in a 3 to 5 ratio. So you actually, without even having a fully balanced chemical equation, can figure out what the ratio of one reactant to another in a redox reaction is going to be by looking at how many electrons one is gaining and how many electrons the other one's losing. All right? Because if I have 3 manganese, that's going to gain 15 electrons, and if I have 5 vanadium, that's going to lose 15 electrons. So the number of electrons gained and lost will be the same. So that's where this 5 to 3 ratio comes from. So why do I point that out? Well, here, let's go to an online simulator. This is an online simulator, and I'll post the link to this. There's one for acid-base titrations as well. It says redox titration in acidic medium. A lot of redox reactions are going to occur best either under acidic conditions or basic conditions. Under neutral conditions, a lot of times they're a lot slower. So acid or base tends to catalyze the reaction. And so this allows you to pick different reactions. So you can pick a reaction between KMnO4 and Fe2+, or K2CR2O7 and Tin2+, or iodine and S2O3 2-. And they actually give you an equation down here. But even if you hadn't been given an equation, if you just knew the reactants and products, you could figure out what the ratio of the two was. So in this simulator, what you can do is tell it, all right, I want to add more of my titrant. And it'll add, you can see the little animation adding a little bit more. Might help to turn the lights out. And I would keep titrating until I saw a visible change. All right. Now, my first pass of the titration, definitely the visible change occurred by 33.5 milliliters. So next time I'm going to stop and slow down when I get close to there. Maybe I'll stop at 30 milliliters and slow down and add dropwise, so I can pinpoint, all right, when does the change occur. So this allows you to actually just repeat it. In a lab setting, you actually have to go get fresh solutions and dispose of everything properly. So here, let me add up to 26. We're still good. 28.5. 29. 30. All right, 32. We saw last time it was somewhere around here when the change occurred. So I'm just going to keep adding drops until we see the change occur. Now what's happening in this reaction is KMnO4 is purple. Oh, there we reached the end point, 32.7 milliliters. So go ahead and try and calculate now. If it took 32.7 milliliters of this KMnO4, we're told the molarity of the KMnO4 is 0.1809 molar. And the volume of Fe2 plus was 25.00 milliliters. And there's our balanced chemical equation. Let's go ahead and see as a class. This will allow us to actually put in our calculated molarity of Fe2 plus, and we can see if we're right. The reason for the color change there is KMnO4 is this purple solution. As you're adding KMnO4, if the Fe2 plus is in excess, then all of the KMnO4 gets used up. And so you're adding MnO4 minus, and it's not changing the solution to purple. But once you have used up all your Fe2 plus, that next drop of MnO4 minus you add stays purple. And so that's why we're seeing that color change there. Okay, I did the calculations to figure out number of moles for Fe2 plus. How many moles does that work out to be? Who's got it for me? 0.295. 0.0295 moles of Fe2 plus. All right. Now I'm estimating in my head. Does that number make sense? Well, 0.1809, if I'm estimating, is about 0.2. 0.2 times 5 is going to be close to 1. So 0.18 times 5 is going to be a little less than 1. So I'm multiplying 0.0327 by a little less than 1. So 0.0295, a little less. That number does make sense. So now I just take that number and divide by the number of liters, which was 25 milliliters. So multiplying that by 4, and I should get 0.11, or sorry, 1 point, multiplying by 40. So 1.18. All right, let's see if the simulator agrees with us. Correct. All right. Go us. Great job, team. All right. What questions do you have about titration or any analytical techniques? I said at the beginning, this is all just stoichiometry, but you just need to become familiar with some of the terminology, like endpoint, or for gravimetric analysis, like, okay, why are we filtering and weighing? Once you weed through that terminology, these are just stoichiometry problems. So they're just following those same 3 steps. Go to moles, use a balanced chemical equation, and go back to what you're asked for. Question? So the question is, if you're doing titration in real life, would you need to seal the flask? Not this one, because there's no reaction that's going to occur with the air necessarily. Now, there are things that will get oxidized by the air, and so sometimes you would do these in a vacuum or in an environment where it's filled with just inert gas like nitrogen or something, so that there is no reaction with the air. Or sometimes you would just want to work relatively quickly so that the air doesn't have time to oxidize your reactant. But yeah, so there are cases where you would need to carry one out in the absence of air. But for most, no, there's no need to. Other questions? All right, let's do a quick check to see if we met our objectives. So let's read these. Learning objective 1.1. The student can justify the observation that the ratio of the masses of the constituent elements in any pure sample of that compound is always identical on the basis of the atomic molecular theory. Take a moment to process. That's a lot of language. Oh, did I not include these on the slides? Oh, all right, we'll just take a moment to read them on the board. I was trying to save paper, I guess. All right, so how do I translate How do I translate this into understandable language? Anyone want to give it a crack? All right, question. All right, question is, what is constituent elements? Constituent elements are just the elements that constitute something. In other words, uh, constituent elements are the elements that make up something. So, for instance, in water, the constituent elements are hydrogen and oxygen. That's all that fancy word is saying. All right, well, if no one else wants to try and translate, here's my best shot at translation. Uh, what this is saying is, in a compound, there's going to be a fixed ratio of mass of one element to mass of the other element. You are expected to recognize that that's because there's a fixed ratio of atoms of one element to atoms of the other element. So on the basis of atomic molecular theory, the idea being, okay, molecules or compounds are made of atoms. We're making the mental leap to say that if the ratio of mass of hydrogen to oxygen in water is always the same, it's always a ratio of 2 grams of hydrogen for every 16 grams of oxygen, then the mental leap is, oh, that means it's because there's 2 atoms of hydrogen for every 1 atom of oxygen. And this goes back to the beginning when we talked about, if you look at the beginning of these lecture slides, we talked about mass percentages in a compound and how you can use that to get the empirical formula. So the mass percentage is how much mass of each thing there is. The empirical formula tells you the ratio of moles of one to moles of the other. Any other questions on that first objective? Notice that's actually their first objective for the whole year. Like, this is 1.1, 1.2. These are their first 3 objectives for the course as they would lay it out. All right, learning objective 1.2. The student is able to select and apply mathematical routines to mass data to identify or infer the composition of pure substances and or mixtures. Digest for a moment. So what does that mean? All right, able to do stoichiometry, specifically what kind of problems? Empirical formula problems. So at the beginning when we said determine the, here's some data, determine the empirical formula. You're applying a mathematical routine to figure out the ratio of one element to another element and then putting that specifically into an empirical formula. Also analyzing mixtures. We'll do some stoichiometry problems where we analyze mixtures as well. All right, 1.3, the student is able to select and apply mathematical relationships to mass data in order to justify a claim regarding the identity and or estimated purity of a substance. Anyone want to translate that? All right, using the coefficients in a chemical reaction, doing some calculations, and then being able to say, well, I think this compound is probably pure, or this compound's probably not pure. Remember we talked about when you do an example, you can determine what the expected result is based on stoichiometry. So here was an example where we had a bottle of potassium chlorate. We ran a reaction. We had one expectation. We said we'd expect the mass to be 9.12 grams after we heated it. And then afterwards, if it was 10.05 grams, that would make us question its purity. So I think there's two parts to this objective. The first part saying make a claim regarding the identity of a compound. So if you had a compound and you were unsure of what the ratio of one element to another was, you could do an experiment and get the ratio and then say, oh, this is what the empirical formula is. So it kind of relates to 1.2 in that regard. And then estimated purity, I think that is matching up your expectations with what actually happens, and then saying, you know, making a claim regarding whether something's pure or not. Questions about 1.3? All right, 1.18, the student is able to apply conservation of atoms to the rearrangement of atoms in various processes. All right, balancing chemical equations is one. Another one, I think this goes back to chapter 10, drawing those particle representations and following conservation of matter in a particle representation. So, you know, there's different levels at which you want to make sure you're following the conservation of matter all the time. One is just balancing chemical equations. Another is making other representations that show that atoms don't get created or destroyed. All right, 1.19, the student can design and or interpret data from an experiment that uses gravimetric analysis to determine the concentration of an analyte in a solution. All right, we did a couple examples. So that's gravimetric analysis. Student can design and or interpret data from the experiment that uses titration to determine the concentration of an analyte in a solution. Also what we just did. And then 3.9, the student is able to design and or interpret the results of an experiment involving a redox titration. We'll actually do one in the lab at the end of the year when we come back to redox reactions. I think it's a good kind of tie things back for later. But we just did some examples of that. What questions do you have about chemical analysis before we call it a day?